Hi, my name is Mika Brown. I'm a senior physics student at the University of Arkansas, set to graduate in May of 2026. And here's a look at my summer research experience at the University of Florida SURF-REU program. And I've been working within the Department of Astronomy with Dr. Jason Dittman. My project focused on determining how well the James Webb Space Telescope can detect trace molecules in the atmospheres of exoplanets or planets outside of our own solar system. JWST is the most powerful space telescope ever launched, and it's already produced the highest quality data we've ever seen for studying exoplanet atmospheres. I wanted to explore the limits of this instrument, specifically which molecules JWST can reliably detect and which ones are too faint or ambiguous to confidently identify. And this is an important step in assessing the habitability of these faraway exoplanets. I focused on a specific type of exoplanet called a hot Jupiter. These are large gas giant planets like Jupiter, but they orbit extremely close to their host stars. This makes these planets have really high temperatures, and this makes them easier to study using light that filters through their atmospheres. To try and investigate how well JWST can detect molecules in these hot Jupiter atmospheres, I used the University of Florida supercomputer called Hypergator. With Hypergator, I generated about 390,000 synthetic transmission spectra using a Python radiative transfer package called Petit RadTrans. These synthetic spectra simulate what JWST might observe under different planetary conditions, like changing temperatures, cloud coverage, and chemical composition. Then I trained a machine learning model, specifically a 1D convolutional neural network, to look at those spectra and identify which molecules are present, such as water, carbon dioxide, or methane. The goal was to figure out which molecules JWST can detect clearly and which ones are harder to spot due to weaker signals or overlapping features. The initial results were promising. For 7 out of 10 of the molecules, the model could accurately predict molecule presence for a minimal amount of noise. However, the model struggled with carbon monoxide, sodium, and hydrogen sulfide. This could be due to more subtle and overlapping spectral features. Additionally, the model performance suffered when adding in increasing noise, reflecting real-world observing conditions. When 5% noise was reached, model performance performed poorly. So an initial result is when planning JWST missions is to get a signal-to-noise ratio on the planet better than 5%. Future work that I would like to do is taking into account chemical equilibrium, expanding model parameters, and changing molecular abundances. Overall, this summer I ended up learning so much, not just about exoplanets and astronomy, but also about coding in Python, machine learning, using the supercomputer, learning how to read literature, and also seeing how research really works. I wouldn't have traded this experience for the world. Thank you to the University of Florida for funding the SURF-REU program, as well as the University of Florida Department of Astronomy and the National Science Foundation. Thank you to Dr. Jason Dittman and his group for their mentorship, and to Mike Nazareth, Krista Smith, and Dallas Pedersen for coordinating the SURF-REU program this summer.